Hi, this is the sixth video lecture of the semester. We're going to be discussing the idea of matrix notation, something we're going to use a lot in this course, and then just briefly summarize what we've covered in chapter one. So if you recall, we can define or describe our quantum mechanical system with some ket. In general, for that ket can be written as a linear combination of our basis ket. So in our spin 1/2 system, we use the spin up and spin down states as our basis vectors, and you can write this ket or the general state as just a linear combination of those. And these coefficients A and B can be written as the inner product or the projection of that generalized ket onto that basis bra or onto this basis bra. What that means is we really only need two complex numbers for this for a state in this two-dimensional Hilbert space to represent that state vector. So with matrix representations, what we do is we describe these kets as column vectors where the elements are those coefficients, A and B. And you see this representation captures all the information of our ket notation we've been using previously. The one thing that we have to be careful about with this, though, is we need to be clear on what basis vectors we're describing our system in. So in this case, where we're using the spin up in the z direction and the spin down in the z direction as our basis kets, we're in what's called the z representation. So that A, it can't be ambiguous which basis vector we're applying this to. And this is going to be the spin up in the z direction, and the B is going to correspond to the spin down in the z direction. So if we just comparing what we've been discussing so far with our generalized ket notation and now our matrix notation, we have the ket the general ket written as a linear combination of our basis kets, or in the matrix notation written as a column vector. If we consider what a general bra might look like, if you remember, we just use our basis bras and take the complex conjugates of these coefficients. In the matrix notation, this has to be a row vector instead of a column vector. And again, we're just taking the complex conjugates of these coefficients. And the reason we do this as a row vector instead of a column vector is so that we can actually take the inner product. So in our ket notation, we have the bra taking the scalar product with our ket, and if we multiply that out, we have the spin up and the spin up would multiply together to be 1, so we end up with a squared, and likewise the minus and the minus would give us b squared. All the other terms would go to 0, so we get that as our scalar product. In the matrix notation, it's just a column vector, take it multiplied with a row vector, and you get a times a, b times b, and you get the same thing. But it comes out really nicely, just from what we're familiar with matrix algebra, how to do these multiplications and inner products. So some quick examples. The spin up state in the z representation is simply a unit vector 1, 0. And it turns out all basis states are unit vectors in their own representation, which makes sense. These numbers in this column vector are corresponding to which basis vector they're multiplied to. So all basis vectors are unit vectors in their own representation. If we wanted to look at, say, the spin down in the x direction state, which previously we showed was a linear combination of the spin up and the spin down in the z components, this would just be a column vector where we have 1 and minus 1 multiplied by 1 over root 2. And that's what this ket would look like in our z representation. Finally, if we wanted to do the inner product of the spin down in the x state onto the spin up in the z basis, we just take that the row vector corresponding to the spin up, the column vector corresponding to the spin down in the x direction, and do our matrix algebra to get 1/2. So now that we've got sort of the groundwork for our matrix representation of these systems, let's just summarize what we've sort of covered in chapter 1 so far. Starting off with quantum mechanics is probabilistic. This was essentially, you can't predict the definite outcome of any individual measurement. The best we can do is determine the probability of certain outcomes for a given observable. We also saw that the observables or things you can measure in quantum mechanical systems are actually quantized. This was shown specifically for spin angular momentum with the nice Stern-Gerlach experiments where they shot the beam of neutral atoms through a gradient magnetic field, and they saw it split into 2 possible values. And this is sort of what we used these Stern-Gerlach type measurements to sort of lay the underpinning of what's going on and what's interesting with quantum mechanical systems. We also saw that measurements disturb the system. This came from that one, I think it was experiment 3 of the Stern-Gerlach experiments we looked at, where we prepared our state, our beam of particles in a spin up in the z direction. We measured the spin in the x direction, and then put the spin up in the x direction beam into a z aligned Stern-Gerlach analyzer. And what happened was somehow this measurement of the x component of the spin angular momentum sort of erased or disturbed or changed any information we might have had about the z component of that spin angular momentum. They were all spin up. We made a measurement of the spin in the x direction, and now all of a sudden they are half spin up and half spin down in the z direction. So these measurements fundamentally disturbed the system. We also described we saw how we can describe these quantum mechanical systems using a general ket, which can be written in terms of basis kets that are all essentially vectors that exist in some abstract Hilbert space defining our system. So for our spin 1/2 systems, we had a general state that was written as a linear combination of our 2 basis kets, the spin up in the z direction and the spin down in the z direction. Those basis kets had the properties that they were orthonormal, so they are normalized. The inner products with themselves are equal to 1, and the inner products with each other are equal to 0. And they also span the Hilbert space, or they show completeness, which is essentially this. Any general vector, state vector in our Hilbert space can be written as a linear combination of our basis kets. We saw that the spin in the x direction and the spin projection in the y direction are both quantized similarly to the way our spin in the z direction were. There's nothing special about the z direction. We use it as just as a convention as being the typical basis that we describe it in, but x and y have similar things where their spins quantized into units into plus or minus h bar over 2. And if we wanted to write that spin up in the x direction or spin down in the x direction states in terms of our spin up and spin down in the z direction states, or in terms of our z bases, we saw that they were just 1 over root 2 spin up plus spin down, or 1 over root 2 spin up minus spin down. And although we didn't discuss this explicitly in any of our video lectures, example 1.3 from the book follows the same method that we did for our x bases to show that the spin up in the y direction and the spin down in the y direction can be written as these linear combinations of our z basis states. And finally, we mentioned that the probability of measuring one of the results, one of these h bar over 2, or one of the quantized results of our measurement, is essentially the projection of our generalized state vector onto the basis vector, or the basis bra that represents that the measurement outcome of that state squared. So what the probability of measuring a spin up state would just be a squared, because we would take this generalized ket, take the inner product of it with the plus bra, and that would give us just the a, and then we'd square it. And this jumps back to quantum mechanics being probabilistic. If we wanted to measure the spin up of this spin 1/2 system, or the spin of the spin 1/2 system, we couldn't determine the outcome of any individual measurement. They're truly random. The only thing we can say is the probabilities of each outcome, and they're going to be based on these coefficients. So if we map this to more general systems, not just our spin 1/2 systems, we have a quantum mechanical system with some observable, we'll call it A, and the results of that, of measuring that observable, are quantized into a number of possible results. Call them A0, A1, A2, A3, yada, 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 all the way up to A sub n. The measurement of the system, measurement of A, puts the system into a corresponding ket that matches whatever the outcome of that system was. So there's some ket A1 that corresponds to a system that measured that observable A0, A0, likewise A1 and A2. These kets form a basis for our system that have the properties of their orthonormal. So if I take any of those two kets and take any ket and take the inner product with a corresponding bra, I get what's referred to as the Kronecker delta, which is just that equals 1 if they're the same ket, and it equals 0 if they're not, if they're different kets. And they also have the property of completeness. They span the Hilbert space that our system is described in. So any generalized ket can be written as just a linear combination of all of those basis kets. And finally, the probability of measuring one of these outcomes of our observable is just the projection of our generalized state ket onto the bra corresponding to that basis ket squared. And this essentially can be applied to any quantum mechanical system. The details of what these observables are and the kets are all going to depend on the detailed physics of that system, but these rules apply in general. With that, next lecture, we're going to go into chapter 2. We're going to discuss the postulates of quantum mechanics and a little bit more on the detail and math with our matrix representation and how we can actually determine what these measurement values can be and what these kets are in a given system.